Kisley is a chief engineer at IBM and the HSM division, talking about ISO X9 and payment security. And that's not yours. This is. It's not going to.
That looks like it.
Yeah.
It's not full screen.
Not letting me get down to the bottom. There we go.
I'll just give a quick test here. Seems to work. All right, so this is a great size audience. I just want to say thank you all for coming. See, I saw you look back, and I'll take you back to 2021. In the middle of COVID, I presented here, and I had an audience of 1. And so you know that speaker trope where you say, imagine you're talking to 1 person and that'll make it easier? I didn't have to imagine. So all right. And thank you for the rim tap there. So a quick overview here of challenges in standards, my role, and standards you can shape now if you get involved now. And I do definitely recommend that people get involved and work with standards in payment security. So my work with standards, I started with PCI interaction probably 2016, but my work with X9 started in 2018. I started to take over for my mentor and then became the sole IBM representative in 2019. In 2024, IBM has at least 15 people working across 4 X9 subcommittees and several working groups. My role, get the bills paid, very important for working with the standards body. Vice chair of X9F, X9 representative to PCI SSC PIN Assessors Working Group, which is a very informative and interesting interaction with PCI. And you actually have a chance to influence direction there. And chair of the X9 tag to ISO TC 68 SC2. Now, one thing you'll see on several of my slides, I have a key to some of the acronyms. The standards world is just alphabet soup of acronyms. So I do hope that helps. I'm not going to read through the keys, so I'll spare you that, but it is there on the slides. My work with SC2, starting in 2019, I became one of the US representatives to Working Group 11 and Working Group 13. 2021, I became the WG11 convener and was just re-elected to that for another term. 2023, I gained the ability to observe ballots, which is a double-edged sword, and I'll just leave it there. So about standards. Now, a standard is herding cats, and sometimes your herd is gigantic, sometimes your herd's a little smaller. So I certainly have a lot of respect for the folks in the 19790, 24759 creation and recreation working groups, that their herd's gigantic and contentious. So last year I actually had the same picture, and some person said, all the cats look the same. And that's definitely not how standards groups work. Everybody comes with their own perspective. So what I've tried to do is reflect this in the population of cats while starting with the same picture, because like most developers, I'm essentially lazy at heart. So. All right, standards shape a lot of what we do. X973, cryptographic message syntax, just been around for a long time and being updated for PQC. And again, it's everywhere. And it's used in pushing keys using remote key load from banks to ATMs. It's used in so many places. FIPS 203, 204, 205. We've talked a lot about these. My statement on that, again, it will drive device and protocol security updates for at least the next 10 years. X924 and 11568, key management in financial services, produced by X9F6 and TC68 SE2 WG13, referenced by several standards in the financial services security world. ISO 19790 and 24759, I don't have to go into that, I won't. We've had panels and talks on this. ISO 9564, PIN management and PIN security, produced by TC68 SE2 WG13, and it's the PIN block formats used in the global payment system. So critical to our own payment security every time you go to the store and enter your PIN. Standards development process simplified. There's steps that I've skipped here. And again, there's a key at the bottom to some of the abbreviations there on the slide. So standard starts as a new work item proposal at X9. You have a working group vote, then you have an official new work item, and then you have a working group draft that you work with and create. Then eventually, after many rounds of discussion, that will go out for ballot at the working group level. So then you work through the comments from that ballot and you make a decision. Do we go forward to a subcommittee draft, which really entails the next level of ballot that you're going after, or do we go back to working draft phase and do another ballot at the X9YN level or X9F6 level? So at the subcommittee level, then you have another ballot. You work through those comments and make another decision. Do we go backwards? Do we go forwards? And if you go forward, then you have a draft and a ballot at the board level. Usually your changes and comments at the board level are purely editorial. Really the decision at the subcommittee draft level is the most interesting one in practice. You expect technical changes at the working group draft level or working draft level. At the subcommittee draft level, you think as a working group that you've worked out all of the changes. But then at the subcommittee ballot, then you find out if you worked out all the technical changes, and that's when the more interesting decision is, do we go forward or go back from that point? At the board draft, you really don't have any more confusion. You do not expect any technical changes at that point. And then eventually you send it off to ANSI because X9 does not own the website where people buy the standards, and then ANSI puts it on their website. So this is it looks similar, and I did indeed use the same icons, but this is the ISO standards development process. And one thing I didn't mention on the last slide, so I'm going to talk about several standards that are in progress. And you see at the top kind of a key to the standard development process and little red diamonds. And so when we get into the individual standards, you'll see where that standard is in process. All right, ISO standards development process, new work item proposal, and this voting process is very different. So that is voted on by the subcommittee itself. The national bodies all decide, do we want to put in a vote of yes? Do we want to put in a subject matter expert? And the count of subject matter experts is very important to whether it goes forward. You need at least 5. If you get 4, then you will probably, or 4 or less, you'll do probably another round of ballot, and then the work item will either, they'll give up or they'll decide to go in another direction. So 5 is critical to that standard moving forward. Then you have an official new work item, we'll assume success. Then you have the working draft, and you may have working group draft study rounds where you go back and forth on those drafts and actually have ballots, but it's not that common outside of the very large contentious groups. So when you have a working draft that you feel pretty good about, you go to a CD or committee draft study, and that's 8 weeks. You get a series of comments back, work through those comments. 9 times out of 10, you're going to move forward to a draft international standard, and you then have a ballot at that level, which is 12 weeks. Get a series of comments back. This is sounding familiar, right? You work through those comments and then decide, do we go forward to a final draft international standard, or do we go backward and do another DIS round? And again, the DIS round is the more critical deciding one, the more interesting one. One thing that's different about ISO is you have now a limit date and you have no chance for extension. They took away the extension in the last year and a half or so. And so you have a maximum time limit of 3 years, 36 months. If you don't get it done in that time, they will cancel your project. Now, you can take it upon yourself to abandon or cancel and move forward with a new work item, and I've actually been part of a standard where we did that, and you'll see that in a moment. And again, key at the bottom to all of the acronyms on the slide. So standards you can shape now and where they are. I'll start with post-quantum cryptography because that's the huge topic of this conference. And I take it back to, so I did a search. I wasn't there in 2016, but July of 2016, a gentleman named Ralph Poor, who was near and dear to a lot of folks here, brought up post-quantum cryptography in X9F1, and it is documented. Now, moving on to 2017, X9F4 started work on an update to X973, cryptographic message syntax. 2018, in January, the Quantum Computing Risk Study Group had their first call. 2019, January, they published quantum techniques in CMS, so that is TR50 2019. So that X9.73 update that was supposed to address post-quantum algorithms didn't really result at that time into an update into X9.73. It resulted in that TR. But then 2019 February, the Quantum Computing Risk Study Group comes out with their informative report, IR, FO1, 2019, with a risk analysis. And that was just updated, I say just, it was November of 2022, but it feels like it was quite recent. 2022 October, the market readiness needs assessment started, and that work is continuing at the Quantum Computing Risk Study Group. Moving on with current work, so in August of 2024, X9 started a 30-day inventory of standards that will have post-quantum cryptography impact. And so that work is ongoing now, and if you join X9 now, you can contribute to that. Now, the target for completion of post-quantum cryptography standards updates is September of 2025, a year from now. Now that sounds fast, right? That is very fast. So the X9 board approved fast-track authority for the standards that will need to be updated for post-quantum cryptography. X924 all parts key management, where is that? So work started in November of 2022 with the first draft. That is still in the working group draft phase. However, it does need to publish by November of 2025. This is an X9 standard though, so that's a little looser. It's not just going to get canceled as a project like an ISO standard would. So X9.24 is key management, as I mentioned on kind of a summary slide earlier. And this dates back to the 90s. This is an old standard on how you should do key management. It has a sibling, ISO 11568, which was republished in early 2023, and that's driving this update. So additions from 11568, hardware management device definition, independent purpose designation, which will be bound to the symmetric key, and there's a different independent purpose, intended purpose designation, which is intended to be bound to the asymmetric key. Now, X9 has added some encryption methods, designation, and a key block checklist, which is sort of TBD, but the standard's very much still in process. I don't see a clock available anywhere, so sorry, I did have to check my watch. But. All right, X9.139. First draft on this was put up to the working group in June of 2020, and you see that we expect to publish in July of 2025, or hope to publish then. And again, you can see it's a little longer, a little looser standard development process at X9. Context, as some of you might know, the first ATMs didn't even really encrypt data. ATMs used keys loaded from physical devices, and then people invented proprietary key load protocols to load keys remotely. 2012, X9 TR34 was published, and that was actually based on some of those proprietary protocols. Mid-2010, some POI vendors switched to a proprietary elliptic curve algorithm. ATM vendors still use TR34, which is RSA based. You can use that to load an AES 128-bit key, but it's still largely TDES and RSA. But POI vendors switched to elliptic curve, again, proprietary protocols, and they would like to standardize those, and that's the current work. So X9.139 will be the standardized version of TR34. Goals for this, again, add elliptic curve, support AES 256 or up to AES 256, more trust models, and not requiring a certificate revocation list or CRL to be part of the protocol. That was constricting to several use cases. So there are certainly vendors and situations where the CRL is just made up. That's part of the protocol, or static and not really useful. So, and other people very actively use the CRL. Another change, not requiring bind of the key receiving device to the key distribution host. And the reason for that is Tier 34 has a number of steps, including the bind that you start with of the receiving device to the host. And so not requiring that bind will reduce the number of steps. As long as you have a trust model in place and trust between the devices that's pre-existing, you don't necessarily need an explicit bind. X9.143, and so this is potentially the newest update to really talk about. X9.143 was just reopened this year. It's a key block standard. It's based on Tier 31, which was first published in 2005. And X9.143 2021 was the first standardized version of that. The TR31 was turned into a standard, and that's where we can say X9.143 is the first standardized key block in financial services. You can't say that about the technical report, because the technical report doesn't have any you shall do this, you shall not do that, right? So a TR is not binding, it's not a standard. You can't say it's the first standardized key block then in that case. So in 2022, there was a quick update to X9.143. There is a sibling to this document, ISO 20038. And so the scope of this work that we're starting, in October, I hope to have a first draft prepared with some or all of these changes. PQC algorithm identifiers, extra length support for blocks beyond 9,992 bytes, which some found constricting, notably because you can carry private keys in a TR31 key block. And if you can also carry a certificate list that's backing that key, or backing the public key anyway, that's part of the key pair. And once you start putting a certificate list, it gets large. So that's already been constricting. And when we look at post-quantum cryptography and the potential ability to carry certificates of that type in this object, it's going to blow up past that byte count. So then changing the name of the component of the standard called optional blocks. So you look at certificates, they have extensions, and some of those are optional, some are not. In TR31, all of these extensions are marked optional, and that's not really the case. If you look at a key block carrying an HMAC key, the binding of the HMAC key to the hash mechanism should not be optional. It should be required. And so we're changing the standard to change the name, rebranding optional blocks as something that will be a little bit more permanent and binding. We don't have a good name for that. Probably optional blocks that are sometimes not optional, or something shorter. So another change that we're expecting, key type or optional block for the German region to encode certain use cases that they have for their keys. Updated optional blocks. So DA is an existing optional block, and we're adding the ability for that to encode multi-level key derivation. Then domain parameters, DP, will be a new optional block to encode elliptic curve domain parameters, but you can kind of imagine other use cases for it, for certainly people at this conference, right? KC and KP, key check values for the key that wraps the key block and for the key that's carried in the key block. And so when that's an HMAC key, there are new key check value types that we want to be able to represent. WP is wrapping pedigree, and we will update that to allow 4 bytes for actual strength. And so sometimes you look at a key, and if that key has been wrapped by a key encrypting key that is weaker than that key, the actual strength of that key is not as strong as the byte length, right, or the bit length anymore. It's as strong as the weakest wrapping key that's ever been used. All right, X9.148, so a completely different domain, but it kind of gives you an idea of the breadth of X9. QR code protection using cryptography. And so QR codes can encode a lot more data than barcodes or indeed URLs, which is where you see a lot of QR code use these days. However, in a couple pretty huge markets, they're used for payments. Now, if an app reads a QR code, it doesn't need to be a URL or anything that looks like a URL. It can just be an encoding of a transaction. And so that is what X9.148 tries to set out. However, X9.148 doesn't have interoperability. It doesn't specify objects that will be exchanged. So let's say you want to have cross-compatibility between Brazil and China for QR code payment. You don't have that today, and you can't get there with X9.148. However, based on the security framework, there is a work item at X9 towards actual interoperability of X9 payment codes. I'm sorry, of QR payment codes. And you see there a little key at the bottom to how they envision breaking up the QR code with some routing information, a clear transaction header with some identifiers, and then 500 to 2400 bytes of the encrypted payload. Let me check the time explicitly. Sorry about that, I don't have a clock. So 9564 part 5, bridging over to some ISO standards. Work started on this in 2019, February, and as you see, we're looking to publish in February 2026. This is the example where I was saying it's a long-running project where we got to the limit date, couldn't reach consensus, and so it was canceled, and it really sat in limbo for over a year. And then the working group realized we really need to keep this moving. And so put out a ballot, got the SMEs together to restart the standard using the draft largely from before, but with a few changes that were in the last round of comments. And so in February 2023, restart, new draft. And so this will standardize PIN generation and PIN check value calculation, which is actually kind of a new concept that's introduced with this standard. So current state, disk ballot complete. I have a document with a whole series of changes I need to make, and just like 19790, the majority of these are from the ISO editor. It's just making it map to the ISO directives. That's always fun. So, so I kind of gave that one away. I am the editor of this document as well. So the methods that are in the document right now for PIN generation, random, right? You can just generate pins randomly. That's fine. Deterministic method with offset. So historically, pins are generated just deterministically, kind of around the globe, at the behest of the issuers, the people that issue the credit cards. But it's not quite as secure as random PIN generation, and certainly if the PIN generation mechanism devolves to just encrypting or macking the account number, that's really the worst case. So what we've done here in this standard is try to get away from that, and what you see with the first deterministic method, you are encrypting a counter and then which is concatenated with a hash over the account data. And so there are specifications in there of what to include. That counter increments when you reissue the cards. And so that allows you to get past the case where you've reissued a card number and accidentally you've reissued it to someone also named Jones, and you would very likely, if you had a naive approach, generate the same PIN for that set of account generation, for that set of account information. But with this method and the counter and the other fields that you could optionally include in account data, you would generate a new PIN for that case. So then there's another one that's another method that's based on CMAC, HMAC, and then of course PIN offset calculation to deal with user selected PINs, and then PIN check value calculation, which is CMAC, HMAC, essentially of the PIN itself. And that gives you a PIN check value which you would store instead of a reference PIN in a database. ISO 13491 part 1, checking time because we're getting a little closer to the end here. So this is secure cryptographic devices, and we're here at a secure device conference. We've not talked about 13491 part 1. And so in fact, you'll you'll perhaps come in and say, is this even still relevant? Because we have PCI with their own HSM qualification requirements. We have 19790 and NIST certainly using that. We have common criteria. We have a plethora of secure device evaluation techniques on the market. A lot of these actually derive from 13491 Part 1. And the working group had, I'll just say, hours of discussion about whether to move forward with this. And they felt like there was something we could still contribute with this update. And some of that's multi-tenancy, some of that's hardware management devices. So I think it's actually a very interesting update. The next piece of work here is 13491 Part 2. So in ISO, again, I think you saw this in the 19790, 24759. You set the requirements in one document and the evaluation tool in the next document. And that's the relationship here between Part 1 and Part 2. ISO 25186. So this is a new, very, very small standard, but it's, again, another chance to influence. Card security codes generated using AES. So there's not really been a standard for generation of payment card security codes to this point. 5 minutes, thank you. So 25186 actually comes out of an addition to 9564 Part 5 on the last slide, which was rejected. This is one of the changes that was requested in order to restart 9564 Part 5, was to split out card security codes because it's a different scope. It's really a different focus, and everyone said that needs to be its own standard. But I think it will have a very interesting impact and have its own value. So there's one card security code method that's in the standard so far, and this is probably going to look familiar. It's mashed together a bunch of account information and then take a CMAC or an HMAC. Now, what's different here is that we're adding in a time variant parameter. And so that can give you some, well, time variance. You can also use a nonce with it, but you can imagine a case where you're dynamically generating a card security code and serving it to a card that's actually more of a smart device versus a static plastic card. And then, of course, the card security code length itself is being bound into the method. There are use cases where people want to generate 3, 4, 5, 6 card security codes at the same time. And so while that's not necessarily ideal, you can imagine a case where somebody's generated a 5-digit card security code, and the naive approach is you can weaken that by saying just generate the first 3 digits. We don't want that. So we decided we're going to have the card security code length in the method so it's bound to the card security code that's generated. Other standards work, and this is the last slide, so I'm going to go through this. Quick check. 3 minutes. All right. TR56, crypto agility, a method for remote update to terminals. And so this is so you have a lot of POIs in the field that have TDES keys inside it that protect the other keys. This is a method to update those using ephemeral keys that, you throw those away once you've updated the terminal, but you can end up with a terminal that has essentially an AES 128 key as the main wrapping key inside that terminal. So it's put forward by a terminal vendor, and I think there's definitely some wind in the sails here and some expectation that other terminal vendors will use it as well. So, and it would also be nice to allow reuse of a lot of terminals that are in the field now. Other standards in process. So at WG11, there is technical specification 14742, recommendations on cryptographic algorithms. And you'd be surprised how contentious that can be. We're not really a cryptographic algorithms group. We're cryptographic algorithms for use in financial services. SC27 is really from JTC1, SC27 is the cryptographic algorithms group. However, they specify everything. And so the people in financial services don't want to choose between 400 algorithms for different purposes. That just makes it much more difficult to build systems. As much as we're in favor of cryptographic agility, people in financial services and payment want to choose between a small subset. And that's really the purpose of this document, to recommend that subset. Another piece of work, completely different domain, shows you again the breadth of the working group in ISO here. security reference model for digital currency hardware wallet. And so you have central bank digital currency people and hardware people getting together to hammer out how should you specify the security requirements for a hardware wallet that you would carry around and enable digital currency payments. Now you have a lot of, again, device security experts here, but you'd be amazed how contentious this can get. So maybe you won't be amazed, depends on how much ISO experience you have. And then 18960, security controls and implementation guidance for third-party payment service providers. That's at this ballot, limit November of next year. Another very interesting area. We've already talked about third-party service providers in this forum, so this is a standard about how you should deal with them. Now, I do want to say at the end, thank you, and I encourage everyone, get involved. You see the exciting work that we're doing, and your perspective is how these standards get better. Thank you.
Cybersecurity, Dr. Arnab Ray from Abbott Labs. So.
There we go. Oh, there's a mic. Is there a mic? Okay, okay, so first of all, thank you for staying till the end. It's always the guy who draws the short straw who gets the last talk, essentially, in a 4-day conference. So thank you again for being here. I know you've all planes to catch. So this talk is a little different from pretty much every other talk that you may or may not have heard in this conference. So when Bill initially asked me to talk about medical device cybersecurity, I went back and looked at the past talks and said, well, seriously? This doesn't seem to be the right place for me. Said, no, we still want to hear what your perspective is. So this is my company. I'm going to go over it real fast because you can Google this. This is what we do. This is who I am. And again, I'm not much known in this community, but I've written a book on medical device cybersecurity. And so I'll start off with this. And I'm going to try to make this talk be split into 2 parts. One is a very general part, and the final part is a more technical part where I'm going to talk about the kind of challenges that we face in terms of embedded system cybersecurity design, which perhaps will be very relevant for many of you in terms of things that you might want to build business offerings in. Okay, so why is medical device cybersecurity important? Because we've had a problem with it for many, many years. And it's a very simple thing to understand in many ways that unlike somebody stealing a credit card, if you break into somebody's insulin pump and give them an overdose of insulin, or if you get into somebody's ICD and give them a shock, the effect is immediate. It cannot be rolled back. And it is an extremely personal kind of attack. And this has happened before. So I think the most well-known example of this almost happening when the US Vice President's pacemaker was turned off in 2002 because the Secret Service had credible intelligence that there was somebody in the vicinity who was trying to remotely control his pacemaker. So this was during the Bush years, by the way. So there have been multiple presentations of remote control of implanted devices and of insulin pumps. And the reason why they're the ones that usually get into trouble so much is these are the ones that people go home with. So you have an insulin pump and you have an implanted cardiac device in your chest, and so people have a lot of time to play with how they can break into it. Now, this is perhaps the most important thing is that, again, unlike a credit card compromise, a successful compromise can lead to immediate harm to the patient. So these are, again, some examples of little things that you can do, for instance, that could seriously harm a patient. So, for instance, in a hospital, when you're on an infusion pump, let's say a patient-controlled analgesic, so painkillers. Okay, so what happens is, from the centralized server in the hospital, there is an infusion order which is going over the network. All that somebody needs to do is add 2 more zeros to it, or maybe 1 more zero, and that's it. That's the end. So again, all of these have happened in a typically trusted way, and many times it's very difficult to find out where the data has been compromised, and the effect is felt 2 or 3 hops down the road. The third thing is, and this is very important for us, and maybe for many people here too, is that we work in a regulated industry. So it's not just enough for us to make something reasonably secure, but to also have an assurance argument that something is reasonably secure. So that means that we tend to go for extremely mature technologies. And that's the problem I'm going to come to with post-quantum. Is that we have to follow, and what happened 2 years ago was that the Food and Drug Administration, which is the regulatory agency that regulates us, for about 4 or 5 decades, their remit was very simple, according to the law, which was patient safety and efficacy, which means you can't kill the patient and you can't sell snake oil. Well, 2 years ago now, they added a third item to it, which was cybersecurity. So what that does is, it means that technically non-compliance with cyber hygiene is enough for them to take regulatory action, which could be to not approve your device. So that is a huge change in the regulatory remit of the Food and Drug Administration, and that happened fairly recently. And the last thing is because, of course, our customers want cybersecurity. So healthcare, so that's why we have 140-2, everybody knows what it is here, but when I present this in many places, that's where I have to explain what that is. So healthcare delivery organizations, the people we normally sell to, hospitals, because they are also regulated, not by the FDA, but they have multiple regulatory authorities that they fall under, that they are increasingly asking us for transparency and for things like, what crypto do you use? And that is an answer that most companies, like, what is crypto? We don't even know what you're talking about, but now this is all public knowledge. You can go to a hospital and we have to publicly say what key lengths we use, what AES modes we are using. And again, this might seem funny for many people here, but in the medical industry, which is doctor-driven, these are concepts that are extremely new, novel, and sometimes scary. So, and the last thing is cybersecurity is a reflection on a company's engineering and customer focus. So, when you go, and I heard this many years ago, for automotive manufacturers, one of the things that they work really hard is the light system. So the external lighting system. You wonder why? Because when you go to a showroom, that's the first thing you try on. You turn the thing on. They have seen. And if it doesn't work to the way it is, then that's a reflection on the entire. They don't really vroom the car and see if it goes from 0 to 70 in 4 seconds or not. Nobody does that. So it's the small things that matter. Cybersecurity isn't a small thing. But there's these headlines, and these are basically business, well, I wouldn't say business ending, but definitely severe impact to the business when you've had cybersecurity problems, like in St. Jude Medical, which is actually where I work from. That used to be St. Jude Medical. There were some hackers who found vulnerabilities on the implanted cardiac device, and instead of coming to the company, they went to a hedge fund and they shorted St. Jude stock at a time that Abbott was acquiring it from the market. Again, this is all public domain knowledge. You can Google and find out all the gory details. So, summary, this is why we do it, which gets to the more interesting part of the problem. Why is this such a big, big problem? Why can't we solve it? And why can't possibly we can never really solve it. So the first thing is that it is not standard. So these are some of the things, and I'm not going to go into detail over here because I really would like for people to ask me questions more than me talking. So one of the big problems is, and that is maybe, one thing is, of course, it's not, when you go to the doctor, you're not expecting to get hacked. So none of the business is not built around lack of trust. Unlike banking, I'm pretty sure the first bank that was ever built was the first bank that was ever robbed also. So this is not a kind of business where there is a lot of mistrust, as never has been. So cybersecurity is not baked into the DNA of an organization like it would be in an insurance company. So that is one big problem, but the real big problem, and that's why I want to focus for this crowd, is the extremely long lifetime of hardware. Hardware, like unlike the iPhone, their business is selling you hardware every year by calling it, this is the best iPhone ever made, right? That's their business. The software comes for free. See, we are in a business where, and this is the first point, our reimbursement, our entire business model is driven by clinical outcomes only. So I have changed the hardware. The previous version of the infusion pump didn't have a secure element, and now it does. Is not going to get us a single extra cent of compensation from insurance companies. Because security is something that is expected for free, essentially. So the only thing that gets you remuneration is better clinical outcomes. So you have to do a clinical study and show this does better. So cybersecurity is not something that the market is willing to pay for, per se, but it is now expected at an increasingly high line by regulators. As you can see, the FDA can directly now regulate cybersecurity. So they can come and say, you do not have post-quantum crypto, what is your plan by 2035, given that your device is going to be in people's chests for 2040 to support post-quantum crypto? That is a valid question to ask. But who's going to pay for it? I don't know. The second problem is that device hardware has not traditionally been designed for software updates that is needed for patching. So most medical devices are like toasters. Do you ever update your toaster's firmware? You never do, right? Or your microwave, that does have firmware, by the way. You don't, right? Because you buy another microwave. It's $100, you buy another microwave. See, that's the way medical devices have traditionally been. Whenever you need something new, technically you get it again. But when you have vulnerabilities and you're expected to aggressively patch, well, medical devices just haven't been made for it. And for any of you who have ever been through hell updating their Windows machines, you know what I mean by that. You wouldn't want that to happen to your medical device. The third thing is that many legacy medical devices have not been made for crypto. So there is no source of randomness on the device. So yes, on a software update, you can put crypto on it, but guess what's wrong about the picture? The keys are not being randomly generated because there is no source of randomness in the device. And remember that these are many of them are extremely low power devices, especially in the implanted space. The next thing is that patching takes time. So it's not like updating your phone. It is not always on. Most devices are not connected to the internet. Okay. And this means that we as a manufacturer do not have the level of visibility that Apple has to your Apple phones. There's no way for us to push updates. And even the devices that have TCP/IP, they're usually on the hospital network, locked out from the manufacturers. So again, we have no visibility to it. All we can do is hope the hospital tech applies the patch. Hope. Now, the other thing is that where patches are, you expect that if you have a vulnerability, you should patch it within, let's say, 90 days. Well, for those of you who followed what happened to CrowdStrike, you know what happens when you roll out a patch without fully revalidating everything else. Now, in case of the medical device industry, sometimes you have to revalidate 20 to 30 years worth of medical apps that have been built. So for a small code change of one line, it is essentially a year's worth of revalidation. And remember, we are in a regulated industry, so we have to keep extensive paper trail for everything we do. So the timeliness of adoption of patches is also a huge problem. And finally and this slide is it even worth the risk? So let's say you have a vulnerability on an implanted pacemaker, and in order to patch it, you have to ask an 80-year-old person with mobility issues to come to the clinic to get a patch. Is it worth it? Is it worth the overall risk to patients? Or, yeah, nobody's going to try to hack you, actually, realistically. So again, it's not a fleet-wide attack in many cases. So what are the cybersecurity design challenges? And this is really for this crowd. What are the cybersecurity challenges we have is that on legacy hardware, there is no secure storage of keys. So there's no TPM, there is no secure element, and there's another problem. There's, in many cases, no operating system either. So there isn't a privileged level 0 process. It's one application. Everything runs with essentially root. So there's no way of protecting any secret material at all. So that's one big problem. The second big problem is that there is just not computational resource to do crypto. So we are talking about extremely low power devices that are implanted inside a human being and are expected to stay there for 10 to 15 years. And what happens is that there are usually, nowadays, many of the implanted devices come with Bluetooth. Okay, so there is a place to put crypto, the Bluetooth chip. The Bluetooth chip is usually asleep most of the time. If it was awake, then that's the end. So the Bluetooth chip is extremely optimized to be mostly asleep, and just to wake up when there is some kind of communication. It has to be authenticated communication, because otherwise the attack is very obvious what it is. You can basically drain it through Bluetooth wake-ups. So the problem is that the therapy chip is so low power that you cannot basically add, definitely not add in software. You can maybe try to do some things in hardware, but not in software. You cannot add, the firmware size is so small that you cannot add crypto there. So, so you could say, well, add a security coprocessor and offload all the crypto to that. Now there's also a problem with battery life, and then there's a problem with the cost of the device. That comes back to the fact that nobody's going to compensate us for this. So what people are doing now, and then post-quantum came along, was adding things like ECC blocks and GCM blocks in hardware in the therapy chip. So what does that does is, if you add it in the Bluetooth chip, Bluetooth chips are typically flaky. So what happens if the Bluetooth chip goes down? That means you can't do any crypto at that point of time. So either you have a mode in which you work without security, which basically defeats the purpose in the first place, or you have to explant a device or replace it with the death of Bluetooth. So you actually want the cryptographic code verification, at the minimum, to be on the therapy chip. So one way is doing it, of course, is having some of it as gates. Third thing is, again, comes back to the very difficult problem of randomness. First of all, there's a lack of awareness that crypto, just having crypto doesn't necessarily mean you have randomness. Very few people in the industry, remember, we don't have cryptographers on staff. There's an education and training thing also. This is a strange thing for most people in medical device companies. And then, of course, along comes post-quantum crypto, just as we were getting a handle on things, kind of. So the problem right now is, and we, personally, where I'm working, we face this problem right now. So we're kind of taping out the hardware for the next 20 years at this point of time. And this is right at this point that NIST standardizes post-quantum crypto. And there is right now, there's just lack of hardware implementations for things like LWE or NTT. It's too bleeding edge, let's say, for medical device manufacturers. Again, it is not just enough for us to take some solution from somebody and put it in. We have to then show to the FDA that this is sufficiently robust. That is sometimes the problem. We can barely do it with classical cryptography. And now this comes, and I have to think of things 20 years down the line with them having the regulatory authority to enforce cyber hygiene. So they can point to NSA, sign everything by 2030, and said, how are you going to do that? And the last thing that I wanted to talk about, leaving some time for questions, is one of the design problems that we struggle with is that it is, so let me explain what the problem is. So classically, device manufacturers have owned their hardware. They keep very tight control of their hardware. So they do their own ASIC design, they manufacture, they don't get chips just like that. Okay. But nowadays, especially in the connected health space, what we're doing is we cannot have our own hardware anymore. So we used to have things called programmers, which were things that communicate with the implanted device. Now the programmers were Linux boxes. Now, hospitals don't want Linux boxes which are this heavy anymore. They want to have a tablet, and they want to put all the apps on that tablet. So we as the manufacturer no longer control the hardware on which our software is being installed, which means that we can effectively be attacked through root. Okay, there's no way. So let's say we have a private key. How do you store a private key? How do you ensure that the OS is integrity protected when I do not own or have no control over the boot process? And I'm expected to protect my key from the underlying OS as well as my competitor's app running on the exact same platform. And I can't put an MDM on it because I don't own the tablet, it's the hospital's. So that is the challenge at this point of time. So some manufacturers say, oh, we have jailbreaking detection. No, you cannot have jailbreaking detection because the basic problem with jailbreaking detection is all jailbreaking detection is basically a heuristic. You only check certain memory locations because if somebody has control over your operating system's highest privilege process, then no matter what system call you use, it can give you the result you're looking for. Okay, these are not the droids you're looking for, is exactly what the OS can do. So jailbreak protection provides only a secondary control. It does not provide the level of primary control that we require. So the only solution really is white box cryptography. So it is to protect, and again, that's kind of a challenge for the industry as to how to protect a keys. And again, there's another big problem that we have is if you do mobile gaming like I do, mobile games also they protect their private keys and they protect the integrity, so you just cannot go in the memory and change the currency that you have. But they do it by one way. They expect that you are always connected to the internet. If the connection to the net breaks, your game will be interrupted. Now, we cannot do that in a medical app. We cannot presume that they have continuous connectivity because the thing is often done in basements the implantation is being done in a basement where we cannot presume that there will be connectivity throughout. We cannot break a clinical workflow. So we can presume that there's intermittent connectivity at which we can establish a certain root of trust. But after that, there will be periods of time where we cannot continuously monitor things. So this is, in a way, one of the biggest challenges cryptographically for the device community moving forward. And so I'm kind of at the end of my presentation, which leaves five minutes for questions.
Oh, you're going to go first, right?
I was too late to ask a question in the last session because I didn't run to the microphone, so I'm running here. You explained it on medical devices. It can be that the resources are very constrained. You're worried about deployments of post-quantum cryptography being too heavy for those devices. I was wondering if perhaps it might be necessary to use only symmetric key cryptography, like no public key cryptography on those devices.
So the problem with, so how would you start off with the symmetric key on the device, right? It's a key distribution problem at that point in time.
Yeah.
So when you manufacture things, right, you provide one image. So you don't want to have the same AES key on everything, right? So you have to have asymmetric. The identity has to be asymmetric. So that's the thing. You cannot have a global secret on hundreds and thousands of medical devices. That is even worse.
But a different secret on every device, but of course there's a key management issue that goes along with it.
Yes,
right?
It's the key management issue that goes on with it, and that we cannot handle. So AES as the identity is not feasible. Yeah, of course we will negotiate it. That's standard, obviously.
But of course, the
it
key
has to be
management
asymmetric.
issue is on the side of the server, right? The server needs to keep track of all the keys to the device.
So we don't have a server, as you said, so we cannot keep track. These things go in and they're isolated. We lose visibility of it. It's not like a cell phone. Okay, that's the thing. We provide it and it's gone. We have no visibility. And again, there are certain use cases where we do have visibility. When I say we, I can't speak for every device that's out there. The real protection, honestly, in face of post-quantum is a realistic argument. The thing is that for many of our devices, the lifetime of the device is going to be 10 to 20 years, or at least, so even if you have I've forgotten what it is called, but you know, if a quantum computer cuts down the scale from cosmic scale to maybe 100 years, the real argument is, well, our device or the person is not going to live for 100 years. So there's nothing here that has that kind of store and use later. These are not military secrets, right? These are intrinsically linked to the health of a patient or their PHI. So that is the real protection, and that is really what the industry is going to use ultimately as their threat mitigation. But still, one doesn't want to get down to that kind of time-based, risk-based argument. One wants to enforce the best quality of cyber hygiene. Just like we support ECC and ECDH at this point of time, we want to support 203 and 204.
Okay, thank you.
I'll be quicker. I was Googling my answer, so now maybe I'm further along now than I used to be. But it looks like the FDA somehow regulates or provides a little bit of insight on software as a medical device. At least what Google has revealed anyway, but are there any working groups where cryptographers can come in and perhaps provide insight for secure enclaves, for, you know?
So again, I cannot speak for the FDA, but in general, cryptography to that extent is not something that FDA has ever published guidance on. So the level of guidance has been use authentication or use FIPS-approved cryptography, or use NIST-approved cryptography, I'm sorry. So that's been the level. Now, sometimes when you have submissions, they might give more detailed feedback if somebody using DES at this point of time, or they're using SHA-1 for signing, they may say something. But in general, they do not get down to the level of crypto suites or stipulation of secure elements, at least at this point of time. Whether they want to do it, I cannot comment.
Are there any performance requirements for this kind of operations, for the crypto?
Are there any kind of what I'm sorry?
Performance requirements.
Yes, of course. So, I mean, in terms of when you say performance requirements, you mean, for us, the biggest thing is battery life. So we are optimizing for two things. We're optimizing for battery life, and we're optimizing, so first is battery life, and then we're optimizing for space. Now, some medical devices don't optimize for battery life because they're connected to the wall, okay, in hospitals. But they're possibly optimizing for space because, again, I cannot give an industry-wide answer to it, but the devices that I personally handle, it's battery life because I handle only implanted cardiac devices. And they're becoming smaller and smaller. And I mean, if you look at implanted cardiac devices from 20 years ago, they were this big. Now they're the size of a small battery, and there's a reason for that.
Okay, so the throughput of the number of operations per second is not a matter because, as I assume that there's not many of this kind of operations on these devices?
So time is important for two things. One is, of course, the patient experience. And in many cases, so let's say that verifying a firmware update takes 5 minutes. Let's presume with post-quantum. I optimize for space and I get 5 minutes. The thing is, in many cases, the communication where you don't have Bluetooth is inductive communication, which is magnetic communication. You touch it to the chest of the patient. So you have to presume the patient doesn't essentially move for 5 minutes. If it moves, then the firmware update is broken, right? So there is obviously a performance, a code update has to be in seconds. That is the thing. It's not something which happens all the time, but it has to touch the patient continuously.
Thanks.
Strange considerations, I know.
I want to thank you for your presentation. That was very interesting, especially for a person who works in networks and other type of things. To know the difference between your field and the general networking field, it was really, really eye-opening. So to me, to see that you can do software updates at will, right? You can even schedule it for that matter. So that was very interesting. Thank you for that. So my question is, who makes sure that the update, that the devices, because the devices are from different companies and different strategies they follow. So who makes sure, which organization makes sure that they are applied, they do the right thing by going to the NIST approved algorithms or NIST algorithms?
The Food and Drug Administration.
So do they have some kind of a lab which comes in, the crypto type of labs which come and do this? Is there an equivalent lab?
No, so they don't certify things.
Okay.
So again, when I say the FDA, remember that different countries have different regulations. Since this is US, I'm focusing on the US. There is, I think, Singapore is perhaps the only country that I know that has a system where you can basically test and get a sticker of like level 4, level 3, level 2, level 1. The FDA doesn't do it. No other country does that. I think it's only one country. It's either Singapore or Taiwan, I forget. But no, the FDA does not verify cryptographically that it does what it says it does. There's obviously a matter of trust. Now, what they expect from us is third-party penetration tests.
I see.
So that is basically I wouldn't say a standard, but de rigueur for any submission. So we have to give our devices to pen testing labs who, it's not just crypto, so they use different techniques like fuzzing, attack surface analysis, and it's a fairly involved process, and now pretty much all regulators want to see your pen testing report before they...
So,
Yes, so when you submit, you have to provide a pen test report. That's fairly standard now. And
So-
it's not just often a pen test report. In many cases, it has to be your static analysis reports too. There are many, the FDA asks for a very extensive threat model, which is basically a paper-based exercise, but we have to submit all data flows, every key length, every mode that we use. We have to document all of that. If you don't document, they will create a deficiency and make you answer those questions.
there's no standard for pen testing that you should do these kinds of pen testing? Or
No,
is it just-
there is, no, at this point of time, there is no standard for pen testing. No.
And if there is a major, there's nobody else, so I can ask more questions. So if there is a major catastrophe and then you have a major vulnerability, then how do you recall these things that it's in the market?
So the way FDA does these things is that they have everything is risk-based. So let's say you have a vulnerability, you first have to assess the risk to patient safety.
Right.
So there could be that a vulnerability is CVSS score 10, but it really does nothing to the patient. Or it could be CVSS 3.1, and there actually could be risk to the patient. So once it is unacceptable risk, and remember, this is not just due to cybersecurity, it could be due to a software bug. So this process has existed since time immemorial. So now the FDA basically, and device manufacturers have to do a voluntary recall. So there are different kinds of recalls. It's a class 1 recall, class 2 recall. So some of the recalls are, you tell your patient population, hey, don't do this. Okay.
Yes.
It could be, keep the programmer in a locked box, or update your operating system to the latest version. Or it could actually be, go to your doctor and get a firmware update. So it depends on the criticality of, and that all manufacturers, if it is unacceptable risk, they have to work with the FDA through it. FDA tracks patch adoption. Yes,
Okay.
they do all of that.
Thank you very much again. It was very interesting.